Every time you fry an egg and it slides effortlessly onto your plate, you are relying on a chemical miracle that was never supposed to exist. Before the late 1930s, dealing with scorched, stuck food was simply an unavoidable reality of daily domestic life. The solution did not come from a culinary master, but from an industrial chemist named Roy Plunkett, the accidental architect of the modern kitchen. How did a young scientist working on refrigerator coolants inadvertently create one of the most slippery substances known to humanity? Plunkett's discovery would eventually coat our cookware, insulate our aerospace cables, and even help build early atomic infrastructure. To understand how a single laboratory accident changed the fabric of modern manufacturing, we must look at the world he stepped into. Roy Plunkett was born in 1910 in the small rural town of New Paris, Ohio. His family was far from wealthy, and his early years were defined by the grueling demands of agricultural labor. The physical toll of farming during the early 20th century drove many ambitious young men to seek alternative paths. For Plunkett, that path was higher education, fueled by a deep fascination with the invisible mechanics of the physical world. He enrolled at Manchester College in Indiana, scraping together his tuition by working various odd jobs. His academic brilliance quickly became apparent, leading him to focus intensely on the emerging complexities of modern chemistry. After completing his undergraduate studies, Plunkett pursued a doctorate at Ohio State University. The 1930s were a golden age of chemical exploration, with massive corporations pouring fortunes into research and development. In 1936, armed with his newly minted doctorate, he entered the highly competitive industrial job market. He was quickly hired by the DuPont Company, a chemical titan rapidly expanding its research divisions across the nation. Plunkett was assigned to the Jackson Laboratory in Deepwater, New Jersey. His first major assignment had absolutely nothing to do with consumer cookware or advanced protective materials. Instead, DuPont tasked the young chemist with solving a highly specific and lucrative industrial problem. The household refrigeration industry was booming, but the chemical coolants used in early fridges were often dangerously toxic or highly flammable. Plunkett was ordered to synthesize a new, safe refrigerant gas that would not explode or poison the consumer. This corporate mandate placed him at the absolute bleeding edge of fluorocarbon research. He began experimenting with a specific gas called tetrafluoroethylene, attempting to synthesize it into new, stable compounds. He produced exactly 100 pounds of this gas, storing it carefully in small, pressurized steel cylinders. To keep the highly reactive gas stable before testing, the steel cylinders were packed in solid dry ice. Plunkett and his laboratory assistant planned to systematically test the gaseous contents of these cylinders over the coming days. They had no idea that the intense freezing cold and the raw iron inside the cylinder walls were quietly triggering an unprecedented chemical chain reaction. The stage was set for a monumental mistake that would alter the trajectory of materials science forever. When Plunkett opened the valve on that chilly April morning in 1938, he expected a loud hiss of pressurized gas. What he found instead would defy every fundamental expectation he held about chemical synthesis. On the morning of April 6, 1938, Plunkett and his assistant Jack Reebok prepared to test their first batch of tetrafluoroethylene. They attached a pressure gauge to the valve of the chilled steel cylinder. When they twisted the valve open, absolutely nothing happened. There was no hiss of escaping gas, and the pressure gauge read 0. Yet the heavy steel cylinder still weighed exactly the same as it had when full. Plunkett realized the mass had not vanished, but had somehow transformed entirely inside the sealed container. To solve this impossible puzzle, he ordered the assistant to remove the valve assembly completely. Plunkett then turned the heavy metal canister upside down and shook it vigorously over a laboratory workbench. A strange, slippery white powder drifted down onto the black surface of the table. The gas had spontaneously polymerized, meaning its molecules had linked together into long, incredibly strong chains. Plunkett grabbed a wire and probed the interior walls of the cut-open steel cylinder. He noted that the smooth, white resin had coated the inside of the iron vessel completely. This white powder was polytetrafluoroethylene, soon to be known globally by the trademark name Teflon. Plunkett immediately began subjecting the mysterious flakes to every harsh chemical test available in the DuPont laboratory. He submerged the powder in highly corrosive acids, but the substance remained completely unharmed. He then exposed the white flakes to extreme heat, finding that they refused to melt or burn, even at incredibly high temperatures. Most remarkably, the surface of the powder was virtually frictionless, causing water and oil to simply bead up and roll away. Plunkett carefully documented these bizarre, impossible properties in his laboratory notebook, securing the patent in 1941. Initially, DuPont had no idea what to do with this incredibly expensive, difficult-to-manufacture superplastic. Producing even small quantities required dangerous chemical reactions and extremely specialized equipment. For a few years, Plunkett's miraculous white powder was little more than an expensive laboratory curiosity. The outbreak of the Second World War drastically changed the fate of Plunkett's accidental invention. Deep within the secret facilities of the Manhattan Project, scientists were struggling to contain uranium hexafluoride. This highly corrosive radioactive gas was essential for enriching uranium, but it rapidly destroyed every known pipe and gasket material. The military needed a miracle material that could withstand extreme chemical corrosion to build the world's first atomic bomb. General Leslie Groves learned of DuPont's highly classified new plastic and immediately ordered its mass production for the military. Plunkett's slippery white powder was quietly rushed into service, lining the critical valves and seals of the Oak Ridge uranium enrichment plant. When the Second World War ended in 1945, the military no longer required DuPont's entire supply of polytetrafluoroethylene. The company was finally free to commercialize the friction-free plastic for the civilian market. However, they faced a massive engineering paradox that stalled consumer adoption for years. If the defining characteristic of this white powder was that absolutely nothing would stick to it, how could manufacturers permanently attach it to consumer goods? DuPont engineers struggled to bind the slippery plastic to metal surfaces. The breakthrough did not happen in an American corporate laboratory, but in a small French kitchen. In 1954, a French engineer named Marc Gregoire was searching for a way to untangle his mechanical fishing gear. He successfully figured out how to coat his aluminum fishing line with the DuPont resin to prevent snagging. His wife, Colette, observed this process and suggested he try applying the same slippery coating to her aluminum frying pans. Gregoire developed a precise mechanical process to solve the adhesion paradox, starting by fundamentally altering the raw metal. The factory worker first submerged the bare aluminum pan into a bath of hydrochloric acid. This aggressive acid wash physically etched the smooth metal, creating millions of microscopic jagged craters across the entire cooking surface. With the metal physically roughened, a specialized chemical bridge was required to anchor the slippery plastic. The technicians sprayed a thin, liquid primer coat, which combined the slippery fluoropolymer with a sticky synthetic resin, directly into the microscopic craters. When baked, this sticky resin melted into the jagged aluminum, creating a permanent mechanical grip while exposing its slippery molecules upward. Finally, the pure, non-stick finish could be permanently locked onto the cookware. A final liquid layer of pure polytetrafluoroethylene was sprayed over the primer and baked in an industrial oven at nearly 800 degrees Fahrenheit. This extreme heat sintered the powder, fusing the molecules into the continuous, frictionless dark gray surface we recognize today. Gregoire launched the Teflon Corporation, selling millions of these revolutionary non-stick pans across Europe and eventually the United States. Roy Plunkett watched his accidental laboratory discovery completely transform the daily culinary habits of the modern world. The days of violently scrubbing scorched food off cast iron and bare aluminum were rapidly coming to an end. Plunkett was inducted into the Plastics Hall of Fame in 1973, celebrated as a brilliant pioneer of modern industrial convenience. However, the mass production of his miracle material required the use of highly persistent chemical emulsifiers, most notably perfluorooctanoic acid. Decades later, environmental scientists discovered that these manufacturing chemicals simply do not break down in nature, accumulating quietly in water systems and human bloodstreams globally. The accidental invention inside that freezing steel cylinder birthed an era of frictionless manufacturing, but it also introduced synthetic compounds that will outlast human civilization. Plunkett's legacy is a permanent testament to how a single laboratory anomaly can fundamentally rewrite both domestic life and global ecology. When you consider the permanent environmental footprint left by these manufacturing chemicals, do you believe the daily convenience of friction-free technology was ultimately worth the unseen ecological cost? Understanding the origins of the materials we touch every day reveals the invisible forces shaping our modern reality. Subscribe to our channel to continue investigating the hidden histories and powerful architectures that quietly govern our world.